All right. So the next thing up, we're just going to kind of continue on with some more examples. All right, I think we're on letter H now. So let's say we have the function y equals y equals e to the sine x. We see the function composition going on here. What's the outer function? E to the x, and the inner sine x. Very good. Okay. So if I do the derivative of the outer, what do I get? E to the sine x. And the derivative of the inner is going to be cosine x. And we'd be done. Let's look at some trickier ones. So this is sine of, cosine of, tangent of x. When you look at this, what do we see? Hopefully you see two chain rules, right? So what is the outermost layer? Sine x. The innermost, or the next inside layer? Cosine x. And the innermost, tangent x. Everybody's okay with that? All right. So let's write it. I'm going to write it like that just for a moment. It's because it makes it a little bit easier to see what we're going to do when we differentiate. Everybody's okay there? So when I differentiate, I'm going to have g prime of h of k of x times h prime of k of x. Everybody's okay with that? But to do this part, what do I have to do? I have to do another chain rule, right? So that's kind of what's going on. So this will be like my final version. Everybody's okay with just representing this symbolically, what we're about to do? And again, if that helps clarity's sake, like feel free to do that, especially early on when you're still kind of getting a feel for what's going on. All right, so g was sine. The derivative of sine is cosine. So I have cosine of tangent x. Everybody's good with that piece. H was cosine, so the derivative of h is negative sine. And then k of x is tan x. And then the derivative of k of x is secant squared x. Is there any simplifying I can do with this? I wouldn't. Because you don't have trig function times trig function. You have composition of trig functions, and we don't know how to deal with those. Like, there's not a good simplifying way to deal with that. The best you could hope to do on this is just move the negative sign to the very front, but just leave it as the product of three things. Everybody cool? Let's do another. Okay. Here we have e to the secant 3 theta. Does everyone see a double chain here as well? So the outermost layer is e, the first inner layer is secant x, and the innermost layer then is 3 theta or 3x, either, whatever you want to call it. Everybody's cool? Okay. So the derivative of the outer layer, so nothing changes there, right? Derivative of the next layer, so it'll be secant 3 theta times tangent 3 theta, and then the derivative of the innermost layer is 3. And again, as far as simplifying goes, there's nothing really to do here. The best thing you'd be able to do is just put the 3 as a coefficient, but like, whoop-de-de-doo, right? Nobody's real impressed with that level of simplifying. Okay. How about no, that's not what I want to do. Yuck, Mr. Gulick. Yuck. What do you guys see in here? I think the same thing. I think there's 3 chains. I would start by, though, rewriting it in an exponential form. Everybody's cool? So if I take the derivative of the outside, that's just a power rule. Everybody's okay with that? Then if I take the derivative of the inside, that's going to be the derivative of that piece right there. So I'm going to get 1 from the x, and then I have to do another chain rule, right? Everybody's good with that? But I had to differentiate this piece here in green. I also had to use a chain rule. So there's that. Can you guys see what happened there? What if we have something like this? What do you see here?
X to the 1/2 parentheses.
Sure. You can think about it that way. What's up?
Oh.
This is actually the way you want to think about this, because what do you notice you can do here? You can multiply those exponents together, right? Exponent of an exponent. So to differentiate this, although it maybe at first looked like it was going to be a chain rule problem, algebra was our good friend there and turned it into something that was really easy. Oh, Mr. Kulik. What if we start mixing together product, quotient, and chain rules together? Is that something you're going to have to deal with? Oh, you betcha. So if you look at this, h of s equals s plus 1 to the 5th times the square root of s minus 1. What do you see here? I see two chains in a product. I'm going to use a chain rule for s plus 1 to the fifth, and I'm going to use a chain for square root of s minus 1, right? Okay, so if I apply the product property, I get this. Everybody good with that? Now to differentiate the square root of s minus 1, that's a chain rule. But it's an easy chain, right? So that's the derivative of the outside. What's the derivative of the inside going to be? 1. Excellent. Everybody see that? And then need to do a chain rule on that piece. But again, the derivative of the inside is just 1. There we go. Is everybody okay with what we did there? Oops. That's not supposed to be a 7 down there. That's supposed to be an X. Pretty dumb there, Mr. Bulik. Oh boy, when you look at this, what do we see? How many chains? See 3 chains, a quotient, and a product, right? Take a deep breath. It'll be okay. All right. So what's the first rule that we're going to apply here? The quotient. Yep. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Everybody okay with this? Look. Okay. Now to do the derivative of x plus 2 squared times 3x minus 4x to the fifth quantity, the 100, I need to use the product property. then to do the derivative of 8 minus x to the 7th, that's just a chain rule. Everybody okay with that? And then we're still all over that denominator. I'm going to simplify that to just be x minus 7 to the 14th, though. Everybody's okay with me doing that? All right, so we still have 2 more derivatives to take inside of this mess. So the derivative of 3x minus 4x to the 5th to the 100 is a chain rule. So it's the derivative of the outer, and then the derivative of the inner. And then we have this derivative still to do, also a chain rule. Then I still have all this other junk. So there the calculus is done, but what's the real fun left? There's some decent simplifying that can happen in here. So let's do that. I see some good stuff that can happen. So if I look at this first quantity and compare it with this second quantity, I'll notice that I have a greatest common factor of 8 minus x to the 6th that I can pull out. So I have this here as well as this there. Everybody see that? And then I also notice that I have a 3x minus 4x to the 5th quantity to the 99th as a greatest common factor. So let's take that out. So the 2 blue boxes.
Is it 1 to the 7?
Yep. So the biggest I can take out is to the 6th, right? And then I can take out if I look at the x plus 2's, I can take out one of those. So what am I left with then? That blue box just turns into 8 minus x. And then inside I have the 100. I have the 3 minus 20x to the 4th. I have an x plus 2. All the 3x minus 4x to the fifths are pulled out, though. And I look here, I have 1 3x minus 4x to the fifth left in there. And then I have the 2. And then on the last piece, I have the x plus 2 is gone. I have 1 3x minus 4x to the fifth, and then I have that negative 7. So I'll make that a plus sign. And then I can reduce this. And I probably wouldn't do any more than that. Because any more foiling and distributing, I think it's just going to make a bigger mess. But I was able to do a little reducing. That's nice. Now, who kind of got lost on this? This was a lot, right? A lot to keep track of, for sure. Can I pose to you a different way of approaching this problem? Okay. So what I would do instead, particularly when things start to get complicated, is I'm going to think about this symbolically first. Everybody's okay with that? So I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then g of x, or the derivative of g of x times h of x is a product property. So that's what I'm going to be plugging in, right? Now what I'll do is I'll just take the derivatives for g of x, h of x, and k of x separately, and plug those into the formula that I wrote above. And it's a little bit easier to kind of keep everything straight. And it's a little less symbols to be writing down over and over and over again because it's less recopying to approach it this way, right? Do you guys kind of see what I'm doing? we had a homework problem that suggested that you did the quotient rule in this manner, right? You guys remember that? I think from section, I don't know, 3.2 or something. So now we just fill in the blanks, and we're at the same place we were on the previous one. But I think a little bit more cleanly than we would have before. Hi, Paul. And that's just like less symbols to kind of carry around through all those steps. You know what I mean? What do you think? It didn't make it massively easier. We'll actually look at something in 3.6 that would be a decent approach to do for a problem like this that actually makes it a little bit, I think, a little bit easier because it gets rid of all the product and quotient rules. And you might be thinking, oh, Mr. Gula, can we do that right now? No, not right yet. But that is coming.
Shortcut for a shortcut.
All right. And then one last thing to do here. So we saw this rule. When did we do this? We did this back in like at the end of chapter 2, we kind of discovered this, right? We're now at a good place to prove this now. And the reason we've held off on proving this little shortcut is because to do that, I want to use the chain rule. So a to the x, I can rewrite as e to the natural log of a all to the x. Because what is e to the natural log of a? Just a, right? So that's still just a to the x. Everybody agree with that? So if I do an exponent of an exponent, that just becomes e to the natural log of a times x. Everybody's cool? Okay. So if I do the derivative of a to the x, that's the same thing as the derivative of e to the natural log of a times x. which is a chain rule, right? So we'll have the derivative of the outer times the derivative of the inner always cool with that. Let me put the times one there too. Let me do that. Remember, a is a constant, not a variable, right? Like 2 to the x or something, right? Is that okay? And that piece right there that I've highlighted in yellow was just a to the x. So we're done. Is that okay? All right. I'm going to stop here. I think I gave you guys the 3-4 homeworks last time, didn't I? I'll just change the page so we can see that again. So if you have AP questions that you needed to sort out, you can spend some time doing that. If you want to start on the 3-4 stuff, you can start on that. If you have individual questions for me, you can start on that. While you guys are kind of getting started, I'm going to pass back the Chapter 1 tests and let you guys keep those.